Hello everyone and welcome to the last part of our adventures in linear regression. Part 3 is the model good. Um, so this section is going to be dedicated to deciding, oh, I built my linear regression model. I've got the line. Did it do a good job of predicting the data that I have? Should I be using it to draw more conclusions? So we're going to look at two ways in which you can do that. The first one is going to be residual plots. So this is going to be a way for us looking at error. So you might remember that when you're doing the residual of one value, so like little recall, woohoo, oh that's really thick, hold on a second, that's way too thick, nobody's gonna be able to read that. Recall, a residual is an error where we just take the actual value of the data and we subtract the predicted value. Now that's great if you're just looking at one value, but we want to do it for all the data. So what we're going to do is we are going to be graphing those. So when it comes to the residual plots, we're going to compare the residual to the fits. So this is going to be a graph that compares the residual to the predictions. And what we want to see is in a residual plot is we want to see a good balance of error. By that I mean that you should be seeing some of your data is negative, some of it's positive, and there's no real pattern to it. The reason you don't want a pattern is because that would mean that, I maybe missed something in my data of what was going on. So what you want to see is if we want, and you'll see this more when we do a graph of it, a sort of random looking graph, and we want some points to be above 0, and you'll see why as I start to do this. Above and below 0. You want to see a good balance, because a good balance means that, my error is evened out and like I don't have a ton of error in one spot where I'm really doing bad and some of it in others. So I want to start off with, figuring out the residual for a bunch of points. When you watch your Minitab this week, you'll see how to do this on Minitab, but for now, I'm going to do it using tables. So I've got some data right here, and I've taken the liberty of already doing the first part where I come up with the y-hat, the predicted line. And what I'm going to do now is I'm going to make the predictions for what goes in here. So for y bar, all I'm doing is taking these x values, so like 10, putting it in for x, and then multiplying it by 2.95 and adding 3.82. So when you do that, so multiplying by 10 just moves your decimal place, so that's 29.5 plus 3.82. That'll give you 33.32. And then you just do that for the rest of the x values. So I'm going to do it again for 15, 17, 20, 22, and then 30. So I'm going to pause the video and write those all in here. I also suggest you go calculate these so that you can confirm that you get the same number I do, so that when I unpause, you're right up here with me. Okay, so hopefully you plugged in all these values and you got what you wanted. So again, just a reminder, you're putting in the value for x here, multiplying, and then adding, and that's where these values are coming from. So next up, I'm going to do the residual, and we just talked about this. The residual is when I take the actual data value and subtract what my line predicted. So to do the residual, I'm going to take the actual value of y, 30, and subtract the prediction, 33.32. So for that, oh, that one's easy. I can do that one in my head. That's minus 3.32. That's kind of nice. And so for the next one, we're going to do 50 minus 48.07, which will be 1.93. So I'm hoping you're seeing I've got a positive one, I've got a negative one. So in the first one where I got the negative 3.32, one of the common mistakes people will make is they see a negative and they think, oh man, it means I under predicted, because under means below and it's negative. But that's not actually the case. If you look at this, the prediction was actually bigger than it. So don't make that mistake. Residuals are actually the opposite in order of what you're experiencing. Anyway, so I assume in my heart of hearts you guys know how to subtract, so I don't need to keep writing these. So I'm just going to write the next couple, because what I want to do is I want to graph these. I'm going to show you a residual graph so you can see what these look like, so you know what I was talking about when I said residual plot. Negative 2.32. Okay, cool. Now we are ready to graph. So let me draw an axis so you can get an idea of what goes down on this. So when you're doing your graph, what's going to go down here are your predicted values or your fits. We're going to put y hat down here. And then along the vertical axis, we're going to put the residuals. Okay. Now, when I'm doing residual plots, and where most people do residual plots, they'll put right in the middle here, 0. And usually we'll do a dotted line for the 0 value because that'll help us tell when we've got stuff that's above 0 and below 0. So I go down past -3 and up to 1. So I got to be careful here and make my scale work. 1, -1, -2, -3. And I've got enough room to where I can probably fit that last point in there. And I'll put a 1 here and a 2 here because I've got one that gets pretty big, almost to 2, but not quite there. Cool. And then for my y hat values, I go from 33 to 92. So I think I'm going to, oh, do I want to start at 30 and count up by 30s, I guess? That could work. 30, 60, 90. Not perfectly to scale. My 30 is a little too far over. Maybe I can move that one and pretend I did it right the first time. So then my halfway points are 15, 45, and 75. And that should help me graph this. Okay, cool. So just as a reminder, what I'm graphing when I plot these points are these two against each other, just to keep that in mind. That's why I put them next to each other. So at 33, so a little bit bigger than 30, I'm at -3 1/3, so it's like right down here. We'll pretend that's right. That seems like a good spot. I'll make my point a little bit bigger to kind of fudge it a little. And then at 48, so right halfway in between 30 and 65, should be, where should that be? Oh, that should be like 45, so a little bit bigger than that. I'm almost 2, so right up there-ish. There we go. And then at 53, so almost at 60, we get 1.03, so I'll put that like right there. And then at 62, we're just a little bit bigger than that. And then at 68, so almost at 70, so this is going to be the 75 mark, so I'm going to put it like here-ish. 1.28, so a little bit higher. Here we go. And I'm eyeballing this. When we make Minitab do this for us, it's going to be a much better graph. And then at 92, we're at -2 1/3. So I'm going to call that like here. Now, I don't know about you, but this doesn't look very balanced to me. When I look at this, I've got like a cluster of positive points at the top, and then I've got 2 big negative points at the bottom. This doesn't look very good. I want to have about an equal number above and below to kind of balance things out. So it doesn't look like my my prediction line is doing a very good job. In fact, since these are all kind of clustered together, it looks like it does a better job in the middle than on the ends, right? When I'm extremely small or extremely large, I get more error. It looks like it's farther off, and it's farther off in the other direction. So that doesn't look very good. In fact, that looks kind of bad. And as it turns out, that's one of the things we want for linear regression is we want our residuals to look good, to look balanced. Let's talk about what I mean about that. So as it turns out, there's some requirements for linear regression that we've already done, but then there's a new one, which is down here and not visible on your screen quite yet, but we'll get there. We've already talked about these conditions. Remember, when it comes to conditions for linear regression, these are the requirements for you to be able to use it and use the results to be able to say that this is effective. So if any of these are missing, you really shouldn't be using the results, or you should be very cautious about using them. So the first thing is the quantitative, this really should be variables condition. So when you're looking at this, your response and explanatory variable, and these first 3 should really be reviewed from last time. They both have to be quantitative, are both quantitative. If one of them isn't, you can't use linear regression. And just as a little reminder, the end-all be-all to whether or not you have something quantitative is, does it have units? It must have units to be able to be quantitative. I'm going to try making my pen just a little thicker because this thinner line is just a little too thin. The next thing up is linearity. That means that when I look at the scatter plot, it looks linear. So one thing I always found funny about this condition as a student was that there's no requirement that it be actually a strong relationship. It just needs to look kind of straight. So this is why when we were doing linear regression, and you'll see me do this in the mini tab also, you have to check the scatter plot first, because if it's not kind of straight looking, if it's got a clear curve, you really shouldn't be trying linear regression because, well, it's not straight. It's not a line. Okay. Next up, outlier. So outliers, you really shouldn't do linear regression if you have outliers, because usually they'll throw off your results, make your results look so that your model is either weaker or stronger than it actually is. So we usually will not do linear regression with an outlier. Sometimes you don't have a choice, and you'll have to do it anyway, but if there are outliers, this is the other reason why you should check the scatter plot. Then linear regression, looks like I wrote them. So coming up with a line should not be done. So you really should check these three before you do the line. Now that being said, if you're stuck with the data that you have and it has an outlier in it, you might not have a choice. You might be stuck doing linear regression. Okay, so next up we're going to take a look at the one that you should do after, the equal spread condition. So this is when I look at the residual plot, it should have an equal number of points above and below 0. Okay, good. We just saw this. That was the plot we just did. Should have an equal number of points above and below 0. So if you're picturing the graph, like there's that 0 dashed line. If I've got like 4 or 5 up here, I should have the same number down here roughly. So I should have, I don't know, I want to say like about. It should be close. You shouldn't be like, oh man, I've got a bunch of them up above 0 and just like a couple down below, kind of like what we saw down below. And the other thing we want is we want it to have no pattern. Because pattern means you missed something. Okay. All right. Oh yeah. Here we go. So what you want to look for here is we're going to look at these 3 plots and ask ourselves, does this seem like it's okay as far as residual goes? And I'm going to warn you right now, 2 of these are real bad. So let's take a look at this. So what I want to look for very carefully is I want to see, does it look like it's linear? Do I possibly maybe have an outlier? Or does it look like it has equal spread? So indicate which of these is bads. Okay, so this first one is bad for a very specific reason. Do you see the little hoop pattern here? It's got a pattern, and in particular it's not linear. So this fails to be linear. Okay, see this guy hanging out by himself? And then all these dudes down here? This looks like it fails equal spread very badly because I don't have an equal number of points above and below. Specifically because one of them is really far off from the other because it has an outlier. So this fails because of an outlier. So one thing that's kind of neat is that when you do a scatter plot, if you have a point in there that looks like it might be an outlier and you're just really not sure, when you go to do the residual plot like this, you'll see that it shows up even stronger as an outlier. If it was, it'll do something like this, or it won't. And then in which case you were right, you should have kept it in there. It's not a bad point. Okay. Now, this one in particular is going to be hard to kind of match, but this is what we call a fan pattern. Actually, I want to do a different color for this. Let's do a highlighter. Do you see it? Does they see how it like makes like a cone? I usually call it a cone instead of a fan because like it's hard to see. Now this is bad because that means it starts out really accurate, my error is really low, my residuals are very small, and then they just keep getting bigger and bigger, which means my model gets worse over time. So clearly something has gone awry here. So this one is bad because, well, it just fails equal spread. Has a cone pattern. So you want this to look like a sneeze, random and all over the place, and that there is nothing that really has a pattern in your error. Because if there's a pattern in your error, that means that your model missed something in a systematic way. There's something going on that it didn't see. Okay, pause for a second. So this example covers something that is not in your notes, and I forgot to take it out. So if you want to do this example, it's a fun one, but we don't need to do it. So I apologize for my own error. We're going to move on to the second way we're going to judge, is my model doing a good job? And that's R squared, also known as the fraction of variability or the coefficient of determination. So R squared is kind of special because it is exactly what you think it is. How do I find R squared? I just take the value of R correlation and I square it. I am not joking. It's that simple. Don't convince yourself it's not, okay? So you'll see down here, there's a value of correlation. I am just going to square it. That is all I'm going to do. So don't like freak out when I do that. Anyway, so what does this fraction of variability tell you? Well, it's a measure of how well did your model do in predicting things as we varied through the possible values of y. So this is going to give us, and we are going to interpret it as a percent of the variability. I just put the t as the wrong one. Variability of the response if I could spell, my life would be easier. That is predicted by the explanatory variable, our x. And because I'm writing huge today, so we think of R squared as a scale from 0% to 100%. This is bad. Closer to 0 means I predicted like nothing. 100% is good, although if you get 100%, usually that's a sign that somebody cheated. That your data's no good. So like 90% is great. You predicted 90% of what was happening with your response variable. Anyway, what fraction of the variability in y can be explained by x? Well, that's exactly what R squared does. So I'm just going to take R and I'm going to square it. So 0.77 squared, which is 0.5929. Oops, that 9 looks weird. So if we were to describe this, I would say, oh, about 59.29%. What fraction did it not explain? What did it not account for? Well, whatever's left over. So 1 minus 0.5929, which is 0.4071. So it missed about 40% of what's going on, which ain't bad, but it is not good either. Like I'm barely shooting above 50%. Well, I guess you are kind of close to 60. It's not good. You know, it's okay. I'd call it like mediocre. Is that good? Yeah, that's a good word for moderate. Yeah, I like it. Okay, let's do another one. So let me scroll down. So for this one, the correlation is 0.44. So you're like, that's kind of a weak correlation. Let's see what the variability is. So how much of y can I predict by using x? How much is accounted for by changes in these two and the relationship? Well, let's R square this. So I'm going to take negative 0.44, notice my parentheses and where they're located at, and square it and get 0.1936. Not even hitting 20%. So about 19.36%. Oh, I didn't write the above one as a percentage. Oops. About... Why did I write the 0 first? That was weird. Backwards writing, check. How much did it not account for? Okay, that's going to be a lot more. This is going to be bad. Subtracting in public is kind of scary. Nope, 4. Why did I put 8? I knew it was 4. It's fine. So about 80.64% unaccounted for. Not good. Yikes-a-moo. Not great. I don't likey. No likey. Ew. This is a bad model. So this is one of the reasons why when you have like a mediocre R value, a mediocre correlation, it's your model's not going to do much. It's only going to be able to account for about 20% of the changes you're seeing in Y, which means it's not going to be very accurate. Up here, when we were sitting at about 70%, it's moderate but not great because we were only able to account for about 60% of what's happening. And that's one of the reasons why we want strong correlation before we do our model. So let's take a look at an example using correlation and R squared a little bit, and we're going to interpret the meaning. So a real estate agent fits a regression model to determine the length of time a property has in the market and number of months before it sells and based on its asking price in thousands. And if you know anything about real estate, if you price your house well and at like right about its actual value based on the market, it'll sell faster. So that's what's kind of happening here. But there's other things to keep in mind too, like time of year. In general, houses sell more in the summer because that's when families are moving versus the winter. So there's other things going on here too. So just don't think that this is going to be sufficient. And what we're going to see is like, oh boy, is it not. So what does this R square actually mean? All right, we have actual variables here this time. So about 50%, oh nope, 50.5. I don't want to be bad here. 0.5 of the variability or changes So when you see variability, think varies. It varies a little bit from house to house. They're each a little different, yeah? In time on market can be explained by the asking price. I hope this gives you a better feel for what's happening. Like, so if you have an overpriced house, it might spend a little more time on the market. If you have an underpriced one, well, it's going to move a little faster. That's a little bit of what this is saying here. However, that's not all that's going on because it only accounts for about 50% of what's happening. But that's still kind of big. If you're a real estate agent, you should be thinking asking price. That's the first thing I got to look at. So if you ever watched prices like rise and drop, they usually drop once a house has been sitting on the market for a little bit. They're like, ooh, maybe I priced this a little too high. That's why it's been on here a little bit longer. Let's drop the price and see what happens. And that's one of the reasons people will do that. Okay, cool. Is the correlation between time on market and asking price positive or negative? So this is me bringing up a common mistake. So notice nowhere in this question of do I give you correlation, which is just R, not R squared. So we have the value of R squared. It's 0.505. So the temptation most people will have at this point is they'll just take the square root. But remember, when we square things, we force things to be positive. So there's actually two answers to this, plus or minus. So which one is it? We can't really tell from just R squared. So how you can actually tell is by asking yourself, well, what else does correlation tell me? If you remember back when we were talking about correlation, it really gives you two things. It tells you how strong the linear relationship is between the two, and it also gives you direction. Is it positive or is it negative? And in this case, we have no idea from just looking at that, but we can look at one other thing to tell us direction, and that's slope. So this is going to be positive because slope is, and they're going to match. They both have to be positive in direction then. So I didn't even need to do that calculation there. Well, I didn't even actually do it. It's going to be positive because slope is, which makes sense. You know, the higher my asking price, maybe the more time it spends on market, but not a very strong relationship, so be careful. Okay, so what proportion of variability for time on market is not explained by asking price? Well, I just got to do 1 minus 5.505. Why could I not get that out of my mouth? And we get 0.495, so about 49.5%. Okay, so that about covers it as far as analyzing our model. If you'd like more on that, I do a bunch more graphs in Minitab because creating all those little points by hand, well, you saw my struggle at the beginning. It's a lot easier to do on Minitab. So enjoy that if you would. Thank you and goodbye.